Hello everyone, welcome to the new episode. Here you can see a car center console coin holder which I designed during my master's program for design engineer master's program, and it is modeled using CATIA V5. Actually, I will show this model on my CATIA. Here is the model in the CATIA. And here I have a coin holder designed for placing at center console of the car. This was an assignment I did during my master's program, as I said before. First of all, while designing using CATIA, NX or any such softwares, we must take care of the tree. You can see my tree here. I tried to arrange it clean as possible, and you can see it. There are many things in the tree, like tooling axis, A surface, B surface, C surface, and the various other features like dog houses, screw bows, rib design, etc. There is a part body. Final part body is here, named as coin holder. You can see the symbol here. We must take care of the tree because in industry several persons will be working on the same model. So while transferring our model to some other engineers or designers, they must understand the tree. So it must be properly organized and named. Here you can see my tree. I try to keep it clean as much as I can. If there is any seniors working in the industry, they can also share your views and points. So it will be helpful for the beginners. Just comment below if you have any suggestions or anything like that. So let's enter into the design process I followed for designing this model. First, I received a classes surface from my tutors. If it is in industry, it will be supplied by the styling team. After receiving the classes surface, engineers will look for any surface irregularities or any issues related to the surface. This is the surface I received. This is the classes surface of the center console coin holder, and we will look for any surface issues or make sure if it is following the injection molding principles and other engineering principles. In case of exterior body panels, we will also take care of the safety precautions, especially in case of car bumpers, hood or side fenders, and also roofs, tailgates, etc. We have to take care of the pedestrian safety also. So engineers will take care of that also while receiving the class A surface. And if there is any issues related to the class A surface, they will make a detailed report about that and send it back to the styling department to revise the design. They will also check for the approximate cost of production of the part. For example, in this case, you can see there are two tooling axes. I will unhide this. This is the main tooling axis, and here is a side core axis. So if there are more tooling axes, it will increase the cost of production. So if there are more tooling axes, engineers will request or ask the design department, the styling department, to optimize the design for the cost, reducing the cost. So after receiving the final classes surface after optimization from the styling team, engineers will proceed to the designing of class B and class C surfaces. Here you can see that this is the class A surface, and after that from the class A surface we will create the class B surface, and on the tree the class B surface is highlighted here. And let's unhide it. You can unhide it using the right click, after right clicking and clicking on hide or show, and or also you can unhide it using the space bar on the keyboard. And here is the class B surface, and class B surface will be mostly made after offsetting it from the class A surface for about, in this case it is 2.5 mm, as the thickness of the part is 2.5 mm. And we create this class B surface after untrimming and trimming various surfaces offsetted from the class A surface, and we will create a final class B surface without any gaps or anything on it. After that, we will create the class C surface. You can see the class C surface here. It is a class C surface which connects the class A and class B surface. In short, in brief, the class A surface is a surface which is mostly visible to the customer. So we must take care of the quality of the class A surface. There shouldn't be any irregularities or any imperfections after molding. So the class B surface and class A surface, class C surface will be in most cases will not be visible for the customers, and it is on the class B surface most of the engineering features like dog houses, screw bores, rib, etc. are mounted. After creating this class A, class B and class C surface, we will untrim it. We will trim it together to form a closed surface so that we can form a closed body after creating a part body here. And after creating the closed body, uh, we can check for the draft analysis again. At the initial stage of the class A surface, after receiving from the styling team, we will check for the draft analysis also at that stage to ensure that it is manufacturable using injection molding. In this case, the draft analysis was done for 3 degree, I think, and if it passes, the surface will be in green. At the regions of red, if there are any regions of red or blue, blue is not that problem in most cases. If it is in red, so we have to revise the design in that case. In this case, I set the draft angle for green as 3 degree, and for blue it indicates the 0 degree angle, and if it is less than 0 degree it will be red. If it is red, we have to rework on that specific region, or sometimes on the entire surface or design have to be changed for proper for achieving proper tooling axis. So otherwise we can't create a optimized tooling axis, or we can't sometimes it will cause undercuts or anything like that. You can see on the tree various other features like doghouse, scribbles, rib design, etc. But I created these features only after creating the part body. I will unhide the part body right now. I will hide all this. So you can see the part body here. All these features were created only after creating this main part body, and you can see the doghouse surface which I created. uh, I will hide the part body so you can clearly see how I designed it. This sidecar axis is mainly designed for this doghouse actually. uh, you can see the various surfaces I created for the doghouse, and here is the final result. You can notice that the overall thickness of the doghouse is less when it at the region where it meets with the class B surface. There is a reason for that. It is designed in such a way to avoid any kind of seam marks on the class A surface. So here is a class A surface which will be visible for the customer. So if the thickness is more, it may cause seam marks after creating the part through injection molding. So there are many calculations and other such things we have to do while creating this. I will show such guidelines on my project report in a moment. And you can see a screw boss mounted over this doghouse, and there is also reason for mounting the screw boss over this doghouse. It is also designed in such a way to avoid the seam marks on the class A surface, because if we need to create a screw boss at this height, it will certainly create several problems such as buckling of the ribs or irregularities on the class A surface. Uh, Here you can see, here is another screw boss, and here you can see two ribs here, and ribs have several purpose other than increasing the strength of the body. The purpose also includes locating the part properly during the assembly stage. If there are multiple ribs, we should follow the guidelines while designing the distance between these two ribs. For example, if there are multiple ribs, in this scenario, we have to keep the distance as 2 times of the main wall thickness. For example, the main body thickness is about 2.5 mm. So the distance between those two ribs should be 2 times the wall thickness. So it should be 5 mm or around 5 mm approximately. Let's check that using the measuring tool. It is set as surface only and surface only at selection 1 mode and selection 2 mode. So let's check the distance between these two ribs. You can see that it is around 5 mm. So the design is proper here. Now let's jump to the project report which I made after creating this model. So you will get an overall idea about the several guidelines I followed for designing this for injection molding. So here is the project report I made for this project, and it describes everything, almost everything about this assignment. And if anyone need access to this project report, just comment below. I will figure out a means to share it to you. So it describes everything from ideation stage to the final product design for injection molding, and it also describes some rules we have to keep in mind while designing injection molded parts. Parts which are intended to manufacture through injection molding. For example, you can see that for ribs, the ribs are mainly intended for locating and arresting components of an assembly, providing alignment in mating parts, acting as stops or gates for mechanisms. You can see the rib nomenclature also here. You can see the ribs are always tapered in shape, and rib draft angle is here, and you can also see that tapering here also. You can see that the thickness is reducing when it goes to the top region, and this is the rib thickness at the bottom and rib fillet radius, wall thickness. These are the main nomenclature of the rib, and it also describes the rules for rib creation here. You can take a screenshot of this, or you can comment below if you need access to this project report. You can see the distance we have to keep while designing multiple ribs. The reason is that very tall ribs are prone to buckling under load. If you encounter one of these conditions, consider designing 2 or more shorter, thinner ribs to provide the same support with improved moldability. Maintain enough space between ribs for adequate mold cooling. For short ribs, allow at least 2 times the wall thickness. And that's it. It is the cross section of the part actually. And here are the values which I received on my model, and it is the we should calculate these values before designing these ribs, and here is the guidelines for designing the ribs, and we should calculate it before designing. And for in the case of screw boss, the design should be the overall diameter of the screw boss should be 2 to 2.4 times of the diameter of the screw, and it describes a proper way of designing the screw boss if it is adjacent to the wall. Otherwise, if it is designed like this, it will certainly cause several imperfections on the Class A surface. And here are the general guidelines for screw bosses. Draft angle is generally kept at 0.5 degrees on the wall of the boss, and thickness typically 40% of nominal wall at base. And here are the height to diameter ratio radius. Need to plan ahead for type of ejection, and the type of ejection we are going to use in the molding should be considered while designing the screw bores. And here is the snapshot of my tree actually, and here is the final screw bores integrated with the ribs on it. You can see the tapering of the ribs here, and it is a specific case where the screw bores is designed perpendicular to the main tooling axis. Here it is mounted on a specific kind of doghouse, and it is designed perpendicular to the main tooling axis. In this case, we have to design a side core axis also for these two screw bosses. And here is the design guidelines for the doghouse. This is where doghouse contacts backside of the surface, and it will be on the base surface which it comes in contact with. And here it describes the guidelines we have to follow while designing the doghouse. And here you can see that it is the final snapshot I added on the project report, and it shows that design is successful as the draft analysis. After the draft analysis, the result was fully green, and here you can see that I applied 3 degree as green and 0 for blue. If there is any blue regions on the model, it indicates that that region is 0 degree to the draft angle, and if it is red, it means that it is negative and it cannot be manufactured using injection molding tools. So we have to rework on the model to solve it. Here you can see the rendering I created using Keyshot. It is the class A, it is the coin holder. And in upcoming episodes, we will be discussing more about other automotive parts such as the car fenders, hoods, car bumpers, tailgates, roofs, etc. And also there are other injection molded parts which are designed for an automotive project. I will be discussing about the designing of the various car door appliques. CATIA V5, SolidWorks, NX, and Autodesk Alias are mostly what I am using for as design softwares, and I am mostly experienced with this CATIA and Autodesk Alias. Actually, Autodesk Alias is mostly used by the Class A surface modelers in the industry, and I was not using this CATIA since last few months because I was mostly invested my time on learning this Class A surfacing using Autodesk Alias. So I will be sharing a few models I designed using classes or using this Alias, such as few cars and extra body kits I did using the Autodesk Alias. So thanks for watching.